Good afternoon, everybody. It is 12 o'clock. We will kick off the event. My name is Dale Hansen. I'm the Associate Dean here in the McPhail School of Energy at SAIT. First of all, I want to say thank you to the Society of Petroleum Engineers for allowing us to co-host this event. I do look forward to hopefully at some point through this series being able to welcome participants to campus if the conditions should allow. So, you know, this series on that we're putting on here is really about improving energy literacy amidst everything that is happening in the industry right now, you know, specifically around the energy transition and so on. Today's event provides a platform for presenters from Whitecap Resources, Entropy, and Carbon Alpha to demonstrate their environmental stewardship. And these key players from the industry will do some presentations for us on a major CO2 Flood EOR project, the novel modular carbon capture technology, and characterization of geologic CO2 storage in Canada. So just want to say a little bit about what's happening here at SAIT. So we've been going through a process alongside industry of kind of, you know, rethinking our positioning as it relates to energy and so on. And so we've done some branding work and come up with what is our latest and greatest value proposition. And this is empowering future-ready energy. And what this really means is providing industry with future smart talent and expertise to optimize and integrate all viable forms of energy in responsible ways. And as we all know here on this call, there is absolutely no question that oil and gas is a huge part of any sustainable energy future. And CCUS is really a significant part of reducing the environmental footprint of oil and gas and making it more sustainable long term. So really looking forward to today's presentations, and I am going to turn it over to your moderator, Sharif, to take it from here.
Thank you, Dale, very much for the introduction. I would also like to introduce my co-moderator, Ryan Capri. He's the lead of the SP Calgary ESG series, and he's also a SAIT graduate. I'm going to kick off with some housekeeping items. So this session will be recorded and can be found later on the SP Calgary YouTube channel. All attendees' microphone and video are automatically muted and off for the duration of the webinar. And as Dale mentioned, we are fortunate to have 3 presenters today who will each have a maximum of, not say maximum, just around 10 minutes to present. After such time, they've all done so, we will open up to Q&A. At such time for all questions, so please ask you to put your questions in the Q&A box, not the chat box, and we will do our best to get to everyone's questions in the time allotted. So today we have 3 speakers. We have Adlai Major from Whitecap Resources, Matt Ng from Entropy, and Graham Hack from Carbon Alpha. Our first presenter is Adlai Major, Director of New Energy at Whitecap Resources, an oil-weighted growth company that is recognized for storing more CO2 annually than emitted corporately. Adlai received his BSc in Civil Engineering from the University of Saskatchewan in 1994, with more than 18 years of industry experience, the last 4 of which he has overseen the Weyburn CO2 project of Whitecap. Adlai is undoubtedly a leader in the CCUS domain. Today, he is presenting on the history of CO2 enhanced oil recovery in the Weyburn unit, the role CO2 sequestration plays in achieving net zero, and Whitecap's ambition plans to expand CCUS in Southeast Saskatchewan. Please join me in welcoming Adlai.
Hi, thank you. I'll share my screen. I'll attempt to share my screen, see how this goes. Can everybody see that now? Just a blank screen with a wave on it.
Yeah,
okay.
Yeah, we can see it.
Okay, good. Just got to get this. Okay. My name is Adlai Major. I'm the Director of New Energy at Whitecap Resources. Prior to this role, I managed the Weyburn Unit CO2 flood for 7 years. And today I'll be talking about the role of CCUS in achieving net zero and Whitecap's plans to expand CCUS in the Weyburn Unit. A bit about Whitecap Resources. Whitecap is the 9th largest light oil producer in Canada. In addition to our conventional oil and gas assets, we operate 2 CO2 floods that sequester more CO2 than we emit. Whitecap is committed to best-in-class ESG practices and strives for continuous improvement in our ESG profile and all other aspects of our business. Whitecap is the operator and majority owner of the Weyburn Unit CO2 EOR project in Southeast Saskatchewan. The Weyburn Unit has been operating for over 20 years and has stored more than 36 megatons of CO2. Putting this sequestration project in simple terms, the volume of CO2 stored is equivalent to what 8 million combustion engine vehicles emit each year. The CO2 is safely stored at a depth of 1,500 meters with multiple impermeable caprock layers preventing it from migrating to surface. CO2 EOR has been very effective in the Weyburn Unit, where the reservoir is almost ideal for a miscible CO2 flood. CO2 acts as a solvent, allowing oil to flow more easily and causes oil to swell and expand out of pore spaces. As oil is displaced from injectors to producers, CO2 occupies the space in the reservoir that the oil leaves and is permanently stored. Both oil and CO2 are produced to surface. The oil goes to sales and the CO2 is recycled back into the injectors using large compression horsepower so that all CO2 is either stored in the reservoir or remains in a closed loop. The Weyburn Unit is located in southeast Saskatchewan near the town of Weyburn. It was discovered in 1954 and unitized in 1963 and is a large light oil pool with an estimated 1.5 billion barrels of oil in place. CO2 injection began in 2000 with very strong results. The project is still producing 22,000 barrels a day with less than 5% decline. Even after 20 years of development, only about half the field has been converted from waterflood to CO2, leaving significant upside within the unit boundaries. And there's also an opportunity to expand the unit into adjacent lands in southeast Saskatchewan that have CO2 EOR potential. There's a lot of focus recently on the potential for the growth of CCUS in Alberta, and many people are aware of the 240-kilometer Alberta carbon trunk line. I think few people realize that the Weyburn CO2 EOR project supports an even larger CO2 supply network, including both a US and Canadian CO2 supply. CO2 is supplied by 400 kilometers of large diameter CO2 pipelines from 2 sources. One is SaskPower's Boundary Dam 3 power plant in southeast Saskatchewan, and the other is the Dakota gasification plant in North Dakota. These 2 sources can supply as much as 4 megatons per annum of CO2. The Weyburn CO2 EOR project stores more CO2 on an annual basis than any other project in Canada. And Whitecap believes that expansion of CO2 EOR in southeast Saskatchewan could double that injection rate. And the Weyburn Unit is not only the largest CO2 sequestration project in Canada, but is the largest anthropogenic CO2 storage project in the world, measured by total storage of CO2 to date. So where does CCUS fit into the world's ambition to achieve net zero by 2050? Often you hear in the press that environmentalists question the need for CCUS. The Paris Agreement committed countries to make efforts to limit global temperature increases to less than 1.5 degrees above pre-industrial levels. Net zero emissions by 2050 align with that goal. And these are ambitious targets that involve significant and coordinated commitments between nations and across a wide range of industries. The IPCC special report referenced in the slide above modeled several pathways to limit global warming to 1.5 degrees, and all of those pathways relied on carbon dioxide removal in the order of 100 to 1,000 gigatons to achieve that target. This is a staggering amount when put in the context of the Weyburn CO2 flood, which has injected a total of 36 million tons over a period of 20 years. That lower level, 100 gigatons, represents approximately 2,800 times what we've achieved in Weyburn to date. So I would say there is quite a lot of room for expansion of CO2 or CO2 storage. The IEA produced a net zero report in 2021, which was meant to inform leaders ahead of the recent COP26 meetings. It stated that current commitments fell short of the requirements to achieve the Paris net zero targets and laid out the massive commitment to investment in clean energy required to achieve those goals. If those commitments could be made, no new oil and gas investment would be required, is what they stated. But there are risks if we slow investment in oil and gas, as we have recently, and don't ramp up significantly investments in clean energy. Countries met at COP26 in 2021. In Paris, countries committed to emission reduction pledges, NDCs, that would be ratcheted up every 5 years to attempt to get on track for the Paris targets. The new round of pledges rolled out at COP26 were not enough to make the Paris targets reachable. So one of the key developments from COP26 is that countries pledged to come back with new targets next year rather than in another 5. Many environmentalists considered COP26 to be a failure. However, others point out that it is important to make progress, even if they're falling short of the net zero 2050 ambitions. With respect to Canada's pledge to cap oil and gas emissions at COP26 and the Glasgow Financial Alliance, which seeks to reduce public investment in oil and gas, I think most oil and gas companies do not think that targeting oil supply is the answer. These approaches will not be effective without attacking demand or making massive increases in clean energy investment. In the 2021 IEA World Energy Outlook, we can see that we are in a messy transition with a post-COVID surge in energy demand and underinvestment in energy across the board. Interestingly, oil and gas industry is one of the only sectors where investment is currently aligned with net zero by 2050 targets. But without a drop in energy demand and without the massive investment in clean energy alternatives, we are seeing huge price spikes like the gas price shocks that Europe faced late last year. Whitecap believes that CCUS, including CO2 EOR, can help meet the dual challenge of increasing near-term oil demand and the desire of the world to reduce GHG emissions. Life cycle emissions from CO2 EOR are lower than conventional crudes, and CO2 EOR can displace higher GHG intensity barrels. CO2 EOR also maximizes production from existing reservoirs, reducing the impact of other exploration activities required to meet the current oil demand. Oil revenue can significantly lower the net cost of CCUS. CO2 demand for an EOR project drops over time, and that CO2 will likely be deployed to pure storage and provide steady long-term demand for the captured CO2. So Whitecap is interested in investing in both pure saline storage and also EOR projects. We believe that targeting regional supply, oil supply, such as the possible exclusion of EOR from the Canadian CCUS tax incentive, will do nothing to impact the demand side of the equation and will prevent CO2 EOR from contributing to GHG reduction targets. This slide shows the significant potential for both saline storage and EOR across Alberta and Saskatchewan. High-graded potential EOR pools are highlighted in green, and the basal Cambrian saline storage fairway is shown in blue. Major emission sources are also identified on the map. Whitecap has screened and high-graded approximately 681 pools with CO2 EOR potential, and with a total CO2 storage capacity of approximately 990 megatons. As you can see from the pie chart, this is very small in comparison to the 43 gigatons of saline storage that we have available across these two provinces. Whitecap believes there will be significant CO2 storage in saline aquifers, but we think CO2 EOR provides an excellent opportunity to take the lead in building out the necessary infrastructure. Whitecap is very excited by the opportunities to partner with emitters, capture technology providers, and infrastructure companies to apply our knowledge and execute new CO2 sequestration projects in both Alberta and Saskatchewan. Whitecap recently announced plans for a significant expansion to our Southeast Saskatchewan CO2 infrastructure that seeks to aggregate captured CO2 emissions in the Moose Jaw Regina Industrial Corridor for sequestration in new saline storage and in the existing Weyburn Unit CO2 EOR project. This project has the potential to add up to 200 kilometers of new pipeline and 50,000 horsepower of new compression to sequester an additional 3 to 5 megatons per annum of CO2. This project was announced with Federated Co-op as the anchor emitter, committed to carbon capture. The project also has strong support from the Saskatchewan government and other industrial emitters and is expected to deliver CO2 to the Weyburn area by 2027. This expansion will create a network of over 600 kilometers of CCUS pipeline infrastructure and more than 100,000 total compression horsepower, with capacity to store more than 7 megatons per year in saline storage and EOR. Whitecap is looking forward to advancing this project in Southeast Saskatchewan and to create similar projects in Alberta to expand our CCUS activities. Thank you for the opportunity to present today. I've enjoyed sharing our story with all of you.
Thank you, Adlai. Now moving on to the next presenter. Our next presenter is Matt Ng, geophysicist at the Investor Relations and Commercial team at Entropy. Entropy is a subsidiary of Advantage Energy Limited and a pioneer in the clean tech sector, whose technology has been implemented at the Glacier Natural Gas Processing Plant in Alberta. Matt obtained his BSc in geophysics from the University of Calgary and has procured 13 years of industry experience working for various organizations, such as Shell, Painted Pony, and Entropy. We're fortunate to have Matt presenting here today on his organization's versatile and scalable modular carbon capture MCCS technology, which can be tailored to any industrial emitter seeking to reduce emissions. Please join me in welcoming Matt.
Right, we're on and you can hear me?
Yeah, you can.
Good, all right.
We can see your screen.
Okay, now Adlai and I have some of the same reference material. We didn't totally collaborate, but I'll try to expand. So first I'll talk a little bit about CCS in general. Now Adlai talked a bit about net zero 2050. Now what that is getting to net zero emissions in less than 30 years. And the IEA, the International Energy Agency, actually published, as Adlai mentioned, a pathway to get to net zero by 2050. Now, I won't go through the details of that pathway, but carbon capture plays a fairly significant role in that pathway. And in that, by 2050, we need to get to 7,600 megatons, or that's millions of tons per year of CCS, whereas right now we're only at about 40 megatons. So as Adlai mentioned, we have a long way to go. On the right is public data from Canada's GHG reporting program. This is a summary of Canada's industrial emitters. Now here plotted, categorized by sector and colored by size. And so the blue emitters are emitters less than a million tons per year. And what we see is that 96% of Canada's emitters are actually under that million ton per year threshold. And what's important to know is that we right now don't have a really strong economic solution for those small to mid-sized emitters, and that's what Entropy is trying to tackle. Another observation we have here is that oil and gas and manufacturing are significant pieces of the pie of Canada's emitters. Now, Next map, similar to ADLI's, we have those same emitters on the map, as well as the US emitters, sized and colored by the volume of emissions. And we also have the geologically mapped saline aquifers. Now, saline aquifers, saltwater reservoirs right now are the most accepted storage vessel for CO2, not related to enhanced oil recovery right now. And we're looking for aquifers, which I'm sure Graham is going to talk a lot more about, deeper than 1,000 meters. And what we see here, what's interesting is what makes Saskatchewan, Alberta, and BC prolific in terms of natural resources also makes them prolific in terms of CO2 storage potential. When we look at CCS from a cost perspective, we have the capture component, transport, and storage. And Entropy is trying to tackle making the capture side economic, but storage and transportation are also important to look at. And so having storage options in close proximity to the emitting sources is really important in terms of getting that cost down. Now what is Entropy? It's an interesting partnership between 3 different companies or organizations that are experts in their own field. Now, Advantage Energy is a 50,000 BOE per day, that's barrels of oil equivalent per day producer. We're actually about 90% gas. We own our own gas processing facility. We've actually been sequestering CO2 in the form of pre-combustion CCS for over 10 years. We've actually already sequestered over 500,000 tons of CO2. And we also have in-house earth science professionals that are experts in understanding reservoirs and rock mechanics. We have Allardyce Bauer Consulting. They're a leading a boutique facilities optimization consulting company that has expertise in modular retrofit design and a lot of experience in waste heat capture. Now, in this exhaust or carbon capture process, there's a lot of waste heat, and if that can be leveraged, that can be brought to really lower the cost and make it more economic. And then we also have the University of Regina and CTRI, the Clean Energy and Technology Research Institute. Now with them, we have the advisors, Dr. Raphael Edam and Dr. Paitun Tontawatwithikul, and they're some of the most cited CCS professors in the space. And Entropy is working directly with CTRI to develop, invent high-performance solvents that can be recycled, have better absorption and desorption rates, and again, try to reduce that total cost of carbon capture. So looking at the challenge we have with CCS, the existing pre-combustion projects and EOR projects are fantastic for the space, but 3/4 of the world's emissions are actually from combustion. Combustion where flue gases are in concentrations of 3 to 15%. And for us to really make a difference in growing the CCS profile, we need to crack the nut on understanding and making economic post-combustion carbon capture. And so what Entropy is doing is we're using proven engineering processes, combining it with subsurface expertise and world-leading research to make that full cycle cost less than $50 a ton, and making it a modular, scalable solution where you could start small and grow gradually, where you don't have to tie capital up for a really long time. Our projects, we can go from FID to on stream in 12 to 18 months, able to get tax credits immediately. That's vital for the rapid growth of CCS. Our first advantages, or Entropy's first project, will be at Advantage's gas processing plant, post-combustion. It's currently being constructed. It'll be on stream in a few months, and it will be the largest post-combustion CCS project in the world where it's using gas-fired engines. So to talk a little bit more about Glacier, phase 1, as I said, will be on stream in a few months. It will abate 47,000 tons of CO2 per year. Its initial capital cost was $27 million, so it's still quite expensive, but it's fully funded. We define the break-even carbon price. In our view, that definition is the carbon price required to get a 10% rate of return on investment to be $40 a ton for that project. And we think, there's efficiencies associated with this project. We think in general, this technology can result in less than $50 a ton. Later this year, we have a plant expansion happening where we'll have an integrated carbon capture component with an additional 16,000 tons of CO2 per year. And right away, we'll kick off phase 2, where we'll have an additional 136,000 tons per year. So overall, once these 2 phases are complete, according to the EPA CO2 calculator, that would be equivalent to removing 43,000 passenger vehicles per year. Now, looking at the Glacier gas processing facility and kind of a bird's eye perspective, I've kind of grayed out the existing facility. What this is to show is the modular pieces of our technology, and that it's not disruptive at all to the flow of the facility. And where we are is near the Alberta-BC border, northwest of Grand Prairie. Now, I have a cool diagram here that illustrates and simplifies the process so you can understand what's happening. On the left, we have the CO2 emissions being captured from some kind of emissions source. It goes through a capture unit where it interacts with a solvent. In our case, our high performance solvent that we're going to be testing is entropy 23. The solvent captures that CO2, not over 90% of the CO2. The rest of the CO2 scrub gas goes up, it gets dehydrated. The rich amine solvents, so combined with CO2, figuratively, it's like making soda water, goes through a system, it gets depressurized and heated up and releases the CO2. So then we have a pure CO2 and water stream that then gets sequestered. The solvent, once it releases the CO2, then gets recycled. And so we want to be able to have high efficiency in recycling so that we can reuse and again, make the process as economic as possible. So looking at time here, looking at the challenges and opportunities, what we need to accomplish to rapidly increase CCS from a technical perspective. For entropy, once we can optimize Glacier, we can validate our solvent and improve the technology. We think that there will be a long list of projects that can use the exact same components and have more projects kind of coming. From a skills perspective, we're applying technical expertise in a different way. For example, from a subsurface perspective, right now Advantage specializes in hydrocarbon extraction, and we're using those same fundamentals to model plume migration and understand rock physics and the sensitivities of the rock properties to injectivity. We want to, got smoke, we want to apply post-combustion CCS to any type of emitter and make it a bespoke, tailored process that can really tackle decarbonization in all sectors. From a tenure perspective, CCS is in its infancy right now. Right now, there's a hub model for applying for tenure for the ability to have CCS, and we think that will evolve. From a commercial perspective, some of the things we need in place for CCS to grow are consistent long-term carbon pricing. The projects we have from a lifespan perspective are 25 to 30 years. We need that certainty for CCS to continue. Like any technology, we need grants to be a catalyst to get that initial capital hurdle. And then we need flexible, creative tax credits that can work well, that are efficient, and that for sure are refundable so that there's a return on CCS and CO2 that's being put away. So I think I'm over time. I'd love to hear your questions, and I'll pass it on to Graham.
Thanks, Matt. Before Graham starts, thanks for your presentation. I'm just going to introduce him first. So last presenter, but certainly not least, our final presenter is Graham Hack, Director of Reservoir and Data Sciences at Carbon Alpha. Carbon Alpha is comprised of a world-class team of industry experts, serves CO2 emitting industries, offering cost-effective solutions for carbon capture, transportation, and permanent geologic storage. Graham holds his BSc in Chemical Engineering and Master's of Engineering in Engineering Management from the University of Alberta. He's a reservoir engineering subject matter expert with 13 years in the industry. Graham procured his practical experience working for Encana and Jupiter Resources. Today, we're honored to have Graham present on key considerations for long-term geologic storage of CO2 and further development in Canada. Please join me in welcoming Graham. Thank you.
Hello, everyone. All right, let's see if I can figure out how to share my screen as well.
I still can't see your screen. Yeah, can see it now. Perfect.
You can see it now? All right, fantastic.
Yeah. Thanks a lot.
Excellent. All right, well, I will say that I think I might have the scariest sounding and most technical title going. You know, for a guy sitting in his basement wearing a tie, maybe that's a bit odd, but I promise it's nowhere but up from here. We'll kind of dive in a little bit on the geological storage in Canada here, and really I'd consider this more of a scratching of the surface, maybe give you a bit of an idea of the things that kind of matter here. I realized that I didn't take much of an opportunity to turn or to provide a bit of a sales pitch or a bit of an understanding of what Carbon Alpha is. But really, Carbon Alpha is a relatively new company. We basically came into existence to facilitate decarbonization of existing industrial infrastructure and to help enable energy transition technologies to achieve negative emissions. Really, our focus is more on the transport and storage components of the CCS value chain. And we've partnered and worked with other organizations who have more of that technical capture expertise. We don't house capture technology in the same way that our friends at Entropy do. So let's see if this will navigate forward. There we go. Awesome. So yeah, let's maybe just start with an understanding of storage as part of the CCS framework. So if we think of the value chain, right, we start off with the capture technologies. We then have to move that CO2 somehow, and then hopefully we have a place to put it, so a storage reservoir. And if we dive down into kind of how those elements of the value chain break down into cost, maybe let's start with the figure that I've got on the left there, which is these ranges to kind of show the uncertainty in some of these things. So we see a big range on the capture side from maybe as low as $20 in an ideal world to something north of 150. Transport costs are relatively low and relatively certain as long as you're an onshore operator. And there's some variation in storage costs, but really the economic projects that have gone ahead today are typically exhibiting storage costs less than $25 a ton. So you end up with a total cost that can be fairly variable. And when we maybe look at one illustrative example, you can see that capture makes up maybe about 70+ % of that total cost. Transport's maybe 5 or 6%, and storage is maybe 20-25. So this really highlights to me why there's been so much focus and so many hours and so many brilliant minds focusing on the capture piece. But what I want to maybe highlight a bit is why there needs to be a focus on that storage component, even if it isn't the biggest chunk of the investment pie. So to me, storage is much more than just the last step in the chain. Storage is the piece of this process that really enables successful operation of the project. If you capture all that CO2 and you have nowhere to put it, unfortunately, it likely ends up being re-emitted. Storage is also the main aspect where you can manage that project risk. You can understand the subsurface, you can understand the impact to stakeholders, and really satisfy them that the CO2 is going to be basically reduced and handled in the long term effectively. And it's really that permanency of storage, whether that's via a deep saline aquifer or a depleted reservoir or an EOR scheme. It's that permanency that generates the value in the offset credit market. Right? So demonstrating and validating that permanency is where the rubber really hits the road. On the far side of the screen, I've thrown up just some illustrative uncertainties. And really what I'm trying to show here is when we kind of boil down from the big ranges of what the cost profiles could look like for some of these different components of CCS, we really come away with the idea that uncertainty in how the fluids move through the reservoir, uncertainty in the total storage capacity of that system, you can maybe think of that as pore volume, to use more of a petroleum systems analogy, rise to the top. And more than anything else, what's driving that is the information. It's the amount of data that is available for some of these deep saline aquifers, and our level of control points maybe isn't what it could be as we go to look to screen and characterize these opportunities. I'm not going to say that some of these other components don't matter. There's definitely an impact in having higher purity CO2 in economies of scale in operating a project for longer and in picking the most proximal solution. But finding that high quality subsurface storage reservoir really does have an outsized impact on project economics. And those uncertainties can only really be reduced through the collection of additional data. So all of this really comes down to, we're taking steps along what I would consider a bit of a long and winding path. So I'm very much focusing on the kind of transport and storage solution, not necessarily the capture portion that would precede this. But we look at how long and what kind of activities we're taking as we go from the idea of a storage project through to something that has been developed, operated, closed, and eventually handed back over to the regulator. So if we think about screening, this is the really early stage. I would say a lot of projects are kind of in their infancy and fall somewhere between this screening and characterizing bucket, first couple of years of project life, where really you're looking at defining what a project concept might look like, where storage sites might be, looking at some suitability criteria, really beginning to understand the data that already exists. And then as we get into being able to actually act on the resource, being able to go out and drill new wells, shoot new seismic, really start to characterize, we can get into that site-specific assessment of risks, of containment, capacity, injectivity, basically all the fun stuff that gets the reservoir engineers excited. By the time you get through characterization, you're hopefully almost ready to make an FID on the project. And this is where I think the storage piece differs a bit from the capture, is that there are material dollars to be spent in that characterization phase, which can occur prior to full project FID. So when we're trying to position what order things need to go in, there's definitely an upfront lift that occurs to make sure that that storage reservoir is relevant, is applicable, and is suitable for the project that you have in mind. Kind of run through the rest of these get longer and longer dated. I'd say very few projects or the ones that we've maybe already touched on have actually made it to development and into operations. This is where we're all aiming for, right? If we're going to try to meet some of the IEA targets that my co-presenters have highlighted, we need to get more projects into operation, and we need to basically have viable mechanisms to do so. All right, and I'm so happy that we've all sourced the same polygons. That's very reassuring. On the left-hand side, this is a map of Western Canada with the deep saline aquifers shown on it. And the first time I saw this map, I felt this wonderful comfort that no matter where I went, I was going to find world-class storage potential in Western Canada. And unfortunately, the more we've kind of dug into this, while Canada does have outstanding resource for the storage of CO2, there is a wide variety of quality, right? And that quality comes back to this idea of storage capacity itself, which is shown on the index in the top right, and mobility, basically how those fluids move through the system, comes back to permeability, system compressibility, some of those more subsurface type variables. So while we can almost always find a saline aquifer near an emission source, understanding whether it's the right aquifer, whether it has the right safeguards, whether it will provide the right deliverability or injectivity, those start to matter more and more. Not all of these are going to be created equal. And then what we want to do is, we can see that the subsurface piece really forms an important component, but it's one component of an integrated framework. So I would say that integration is really the key to understanding the risks associated with these geological storage projects. I think of it in kind of 4 modules. We start off with this idea of a project concept, and that's maybe you have an emitter who has some number of friends nearby who all want to pool their emissions and come up with a project idea. In Alberta, maybe that starts to look like a hub. Well, in between that hub and moving forward into kind of subsurface analysis, you need to understand surface constraints. You need to understand the regulatory framework. You need to understand your stakeholders. Maybe there's data quality and availability issues, all kinds of these little aspects that you can see from my title. I'm a reservoir engineer and a data scientist. We're finally getting to the point where we have data. We've got big data. We can start to manipulate all of these spatial layers and begin to highlight go, no-go zones and things that are going to be critical for the development of these projects. So we push that forward as a project design criteria into a subsurface assessment. Now, when we talk about the subsurface, we have our geological, our geophysical, our geomechanical, our geochemical experts. We're going to be looking at how suitable the storage complex is. And I refer to these as storage complexes because the reservoir is just one piece. When we're looking to satisfy the regulator, when we're looking to satisfy stakeholders, it's more than just that one reservoir. There's all of those interstitial layers, baffles, seals, other tangential aquifers that we don't want to come into conflict with. There are the hydrocarbon resources, which we also don't want to impact necessarily for the saline systems. So we'll look at things like depth, we'll look at things like that storage capacity, map them out. And through this whole process, it's really about understanding the uncertainty in these results, right? So I've shown a couple dice on there. This isn't to say that we're leaving it all up to chance. It's more to say that there's risk here, and the better job we can do in understanding the range of scenarios, the better we'll be able to communicate it. So we push those forward then into the first step of modeling. I think we can all safely say that at some point, numerical simulation is going to be where CO2 schemes end up. But since the 2000s, there's been a lot of really good work on developing rapid analytical solutions for plume development, for a lot of the pressure interference between injector wells. So we start to apply that, whether we look at vertical or horizontal development styles, and really try to figure out what's the well spacing going to look like, how much pipeline are you going to need, what's the injectivity in each of these wells, what's going to be that first order constraint on the system, and push that forward into the economics. And so we build up this nice large economic engine from the bottoms up to get an understanding of cost, schedule, a whole bunch of metrics, and then we're able to run sensitivities. Right. And so if there's a change in the subsurface, we make sure to roll that all the way forward into the economics. And if there's a change in our development plan, we can push that back and forth as well. Doing it in this big integrated fashion, I think is very useful. It gets back to metrics that stakeholders care about. So I tried to keep myself intentionally brief. I think we originally said 10 minutes, so I tried to do this in 8 slides, but if you only remember one of them, make it this one, which is that geological storage is more than just the last step in the CCS value chain, that the path to characterizing storage can be complex. It can be long, it can be winding. Canada has world-class storage potential, but not all of those complexes are created equal. And that a dynamic integrated approach to understanding risk can help you increase confidence in your project and hopefully increase the chance of making the right decision, making a higher chance of success. I want to thank everybody for joining us today. And if you have any questions for me, throw them in the Q&A. Otherwise, you can reach out to me directly. Thanks.
Thank you very much, Graham. We have very interesting questions. So I'm going to kick the first one to Adlai. From Tariq Al-Hamami, what is the process of obtaining a storage permit in Canada? Can you please talk about the carbon capture technology used in Weyburn?
I'll talk about the carbon capture technology first. It's different in North Dakota and in Boundary Dam. Boundary Dam, our Saskatchewan CO2 supply, uses an amine, which is similar to what Entropy would be working on, but what they're seeking to do is be much more efficient. Boundary Dam has struggled with efficiency as far as operating costs. The system has been improving year over year. Initially, they had performance problems, but now it's getting to operate a lot more efficiently. But I think most solutions are amine based, and everyone is seeking to make that amine process more efficient with different processes, different chemicals. So that's the process there. Dakota is a gasification plant, so it takes coal and it creates hydrogen from coal and then turns it into synthetic natural gas, and we remove CO2 from that process. That's a fairly unique process. And what was the other question? Oh, CO2 saline storage approvals. Is that?
It's the process of obtaining a storage permit for CO2 in Canada.
I mean, that's sort of in play in Alberta and Saskatchewan. Alberta had a process. They had a run on saline storage. And so they've decided to turn this into a competitive process because there's so much interest in saline storage in Alberta. So you can look at that new process. There's lots of documentation online about that competitive process. And I think everyone here is involved in that in some way, all of the speakers here. And then in Saskatchewan, there is a process in place in Saskatchewan. I would say it's more similar to the process that Alberta had before they turned their changed their process into a competitive process. All of them are going to be looking for, I think, projects that are strong partnerships with emitters, capture technology, experience and expertise in saline storage, financial wherewithal. I mean, they're really all governments in Alberta and Saskatchewan both really have a lot of criteria to ensure that they award pore space to companies that they trust to permanently sequester CO2 for a long period of time, essentially 100 years.
Or more. And I'll just add to that, Adlai, as well, in that important to note that the regulatory framework is early. It's early days and focused in Alberta and Saskatchewan right now on large hub models. The opposite of a hub model would be a point source model, where you could have, as all of our maps show, there are saline aquifers everywhere, and understanding the details of them are important. But limiting it to hubs might limit actual CCS growth. And so we think that we'll start with a regulatory framework with hub models, and it will eventually grow to point source models as well to allow and enable all sorts of emitters to contribute to decarbonization and CCS. Now, what's important to get there is that we can show that we're doing it properly, and we can keep it there permanently. And once we're able to show that, I think those regulations and those approval processes will also evolve with us.
Thank you. So the second question is from Bob Pearson to you, Matt. Do you think that entropy technology can be cost effectively downscaled for application at a compressor plant, especially CCUS recycled compressor facility?
Yeah, that's a great question. And I think that exactly is sort of the wheelhouse of what we're trying to do. We're trying to enable small to mid-scale emitters the ability to do it cost effectively. And we've run models on being able to apply the modular components to as small as 8,000 tons of CO2 per year. That's one compressor engine. We've already scoped out some of our projects that are one compressor or one boiler, for example. So that is what we're trying to do, and that's exactly our goal.
Thank you. Third question to Graham from David Gray. Why has it taken so long to get CO2 pipelines off the ground?
Hopefully my mic's on here. Yeah, I'd say that the biggest barrier to CO2 pipelines in Canada is probably very analogous to the biggest barrier that's existing for oil systems. Is that we haven't done as good a job necessarily of developing stakeholder support for these kind of large scale projects. We're very fortunate to have the kind of infrastructure that exists today for CO2. I think the other piece of that is going to be the necessity, right? There are really only a few operating CO2 storage projects today that require large scale infrastructure to gather and transport that fluid. So as we begin to see Alberta populate with hubs and hopefully point source targets as well, and Whitecap continue to grow their sequestration in Saskatchewan, I imagine we will see an increasing network of CO2 pipelines.
Sound good. Thank you. Next question to Adlai. Is Whitecap looking at any non-EOR carbon sequestration through the Alberta government recent request for carbon hub proposals?
Yes, we're definitely interested in pure saline storage. I think what we've realized, and I hinted at it before, is you see CO2 EOR projects peak in their demand and then trail off. So you've got to line up other EOR projects or saline storage to take that CO2. Once you start capturing CO2, you want to continue to do it for 20 or 50 years. You're not going to want to stop after the demand in an EOR project peaks in, say, 5 to 10 years. We've got a really big project in Weyburn, so we've been able to roll out within that area new CO2 EOR year after year. But in general, it's very difficult to find a really large EOR project that can take all of that CO2 long term. So we really like the idea of getting involved in pure saline storage. And to answer the question about pipelines, pipelines existed to Weyburn because we could make oil revenue from EOR, and that supported the costs of capture and the pipelines. But saline storage, we're all waiting for incentives to be there to encourage emitters to spend large amounts of money on capture and for proponents to spend money on pipelines and CO2 storage. And saline storage is a cost center. It doesn't have revenues, so it needs incentives to happen. And I think we're there now. I think we're starting to see that reducing GHG emissions is very important to our provincial and federal governments. And I think we're seeing those incentives now.
Sounds good. Thanks a lot. Last question from Jim Calbeck to Matt. What portion of the $50 per ton CO2 capture cost do you expect to be CapEx versus OpEx?
Yeah, we have modeled our OpEx to be about $15 per ton for our projects.
Sounds good. And I'll take one more then. So Graham, your ENA and from Bob Person, your ENA and PFID study periods of 1 to 3 years seems very low compared to most mega projects. Why do you assume that you can move that fast, especially in terms of getting planning approvals after characterization?
Yeah, I think that's a great point. There's a lot of variability in those durations. What I would say is that the path that I kind of laid out would not be for a mega project hub, but more for a smaller system. There's definitely an assumption in there that you're able to almost engage with the government. So outside of necessarily the competitive process, but perhaps a project that runs forward in Saskatchewan where the regulatory system has remained a bit more static, or in a jurisdiction like British Columbia, where there's a bit of a separate path forward, which would help streamline some of those planning and regulatory approvals.
Thank you. Off to you, Ryan.
Wow, I don't know what to say, guys. This was a fantastic presentation from all of you here today. Graham, Adelaide, Matt. If I'm honest, I'm a little bit out of my depth here, and I'm sure some of the students feel the same way. One of the audience members actually just asked, will this presentation be recorded? Yes, definitely. You are going to receive an email in about a week so that you can go and view that as well. I know that's something I'm going to be doing to just refresh my mind on everything that we covered here today. I do want to just thank our presenters for being here today and providing this incredibly insightful presentation, right? From Whitecap and the amount of CO2 that you guys have sequestered, just world leaders in that domain, and your plans to expand saline storage of CO2, as well as through EOR initiatives, to Entropy with post-combustion, right? That's, as you mentioned, that's really something that hasn't been considered on a large scale for the most part, and seeing that implemented at the gas processing facility here in Alberta, I think I speak for us all when I say we're extremely excited about that. And last but not least, of course, Graham, the storage component, just didn't even think about it before, and I'm sure many others haven't as well. And to your point, it's so important to minimize that risk for regulatory agencies, for governments, for investors. So I'm really looking forward to see what Carbon Alpha does moving forward. Now, of course, beyond that, events like these, guys, wouldn't be possible without everyone behind the scenes helping out. So just wanted to shout out to a handful of individuals here. We were very fortunate here at the Society of Petroleum Engineers Growth and Development Team to work with SAIT on this initiative. So the Dean and the Associate Dean of the McPhail School of Energy, Lisa Weatherby and Dale Hansen, as well as Jim, Jen, Colleen, and Uwe. With regards to the Growth and Development Team, they've been fantastic. I've had the absolute pleasure of working with Darren Smith. He's our team lead for G&D, as well as Beta, Nick, and Sharif here. Sharif, might look like he was just moderating the event, but honestly, this guy's put in more legwork than I would say anyone else on the team in terms of making these events actually happen and bringing these presenters to you today. So huge round of applause to everyone on the G&D team and everyone at SAIT, as well as our presenters that made this possible. Thank you.